Hey students, Professor Nugent here. Let's look at why control variables work. What we need for control variables to work is conditional mean independence. Because a control variable is correlated with the omitted causal factor, least squares assumption number 1 does not hold for all of the regressors inclusive of the control variable. For example, lunch percent is correlated with unmeasured determinants of test scores such as outside learning opportunities, so it is subject to omitted variable bias. But the fact that lunch percent is correlated with these omitted variables is precisely what makes it a good control variable, right? What we're trying to do here is capture for the variation in outside learning opportunities, where rich kids can afford all kinds of fancy after-school tutoring and the rest of us cannot. So, how do we capture for that? One way is to use lunch percent. So, if least squares assumption number 1 does not hold, then what does? Well, we need a mathematical condition for what makes an effective control variable. This condition is conditional mean independence. Given the control variable, the mean of ui does not depend on the variable of interest. Okay, and this is the key. We are focusing on the variable of interest. We're trying to get a good estimate of the variable of interest. Let's let xi denote the variable of interest and wi denote the control variables. W is an effective control variable if conditional mean independence holds. Here is our expression for conditional mean independence. The expected value of the OLS residual given xi and wi is equal to the expected value of the OLS residual given wi. Thus, we are showing here, using math, that the OLS residual, ui, does not depend on xi, it only depends on wi. So if w is a control variable, then conditional mean independence replaces least squares assumption number 1. It is the version of least squares assumption number 1 that is relevant for control variables. If we consider the regression model y equals beta naught plus beta 1 times x plus beta 2 times w plus u, where x is the variable of interest, beta 1 is its causal effect, and w is an effective control variable so that conditional mean independence holds. And we have this expression so that the expected value of the OLS residual given xi wi is equal to the expected value of ui given wi, so that ui is independent of xi. In addition, we're going to suppose that least squares assumptions number 2, 3, and 4 hold. Then beta 1 has a causal interpretation. Beta 1 hat is unbiased. The coefficient on the control variable, however, will not estimate a causal effect. We will not look at beta 2 and think, okay, if we change w by 1 unit, that'll give us so much of a change in y. No, that's not what we're doing with beta 2 hat. We are just using w to eliminate the omitted variable bias that's occurring for x. That's all that we're doing, and what we're showing here is that if this math holds, then beta 1 will have a causal interpretation and beta 1 hat is unbiased.